Well, hello everybody. It's a pleasure to be here tonight to tell you a little bit about fusion energy. Fusion is a potential energy source for the future, one that would be clean, green, safe, and abundant. It's been enticing scientists since they first figured out what was causing the sun to shine. If we could do it on Earth, it would change the energy landscape. It would perhaps even change the world. So I'm going to tell you a little bit about fusion today and why I'm excited by fusion right now. First of all, I'm going to share my screen. Got some slides here. Here we go. And I'm going to start off with a little introductory video about what is fusion.
Fusion is the reaction happening in the sun and the stars. It's the way the sun makes energy. Hydrogen fuses to make helium and releases huge amounts of energy. Imagine if we could have our own miniature stars producing fusion energy here on Earth. If we could do this, we could produce abundant energy with no greenhouse gases. We wouldn't have to worry about running out of fuels because the types of hydrogen we need come from readily available sources like seawater, and the reaction produces a lot of energy. Just 1 kilogram of fusion fuel produces as much energy as hundreds of truckloads of coal. Half a bathful of water and the lithium in a laptop battery would be enough to cover your lifetime energy needs. Fusion would complement renewables to provide baseload electricity to keep the lights on during peaks and troughs. Fusion could provide industrial heat to clean up dirty industries. Fusion could generate hydrogen as a replacement for natural gas. Fusion could provide clean electricity for transport, or even technologies to scrub CO2 out of the atmosphere. Fusion would power economic development around the world in a cleaner and more sustainable way.
You might have seen there that there's a little bit of a delay between the video, like the sound and the picture. So sorry about that. It's because it's going from the presentation across the internet. So let me tell you a little bit about myself, first of all, and why I care about fusion. So as you heard from John, I'm a plasma physicist. I have a PhD from Imperial College, and I was researching fusion energy. I now work with the private company Tokamak Energy, and I'm UK Director of the Fusion Industry Association. But I'm interested in plasmas in general. I'm also interested in the crossover between science and adventure. I like writing as well. So a long time ago, 10 years ago now, I wrote a small introductory book to fusion energy. And since then, I've also written a book about the Northern Lights, which is also a plasma. So fusion, we're going to be talking a lot about plasmas. And I've also climbed Everest and written a book about the science that enables us to do that, which isn't out yet. Hopefully it will be out next year. Now, I got interested in fusion after my undergraduate degree. So I studied physics, first of all, at Bristol University. And then after that, I took some time out to travel, and I was working and wondering what to do with my life. And when I was away, I think it kind of reinforced some things that I'd been thinking about previously. That is, I'd always been interested in climate change and the energy problem and what we were going to do about that. And then when I was traveling, I did things like I went diving and saw coral bleaching on the reefs. I hiked in the Himalayas and learned about glacial retreat. So I was seeing science in the landscape, and I was still interested in physics. And one day I read about fusion, and I thought, if we could do this, it would be the most incredible thing. It would solve our energy problems. So that got me interested in fusion. So I went back home and I did a PhD at Imperial. And I truly believe that the world needs fusion, and that it will be a really useful thing for us, and it will really help contribute to solving some of our energy problems. So I said before, I'm a plasma physicist, and most people, when I say that, look at me blankly because most people don't know what plasma is. But You're actually quite familiar with plasma. Plasma is just an electrically charged gas, or it's the fourth state of matter. And you know about the states of matter. You know that we have solids, liquids, gases, and now we have plasma. Plasmas exist when there's enough energy in the system to strip atoms apart, like this.
At such high temperatures, atoms break apart and become a charged gas called plasma, the fourth state of matter. Charged particles are affected by magnetic fields. They spin around field lines. So we can use magnetic bottles to trap our fusion fuels.
And you're actually more familiar with plasmas than you think, because the sun is a plasma, lightning is a plasma, flames, neon lights. This is the Aurora, and this is a plasma in a tokamak at Tokamak Energy. So some of those plasmas you're probably already quite familiar with. So now I'd like to talk a little bit about fusion and the energy market and where fusion could contribute there. Firstly, some of the advantages of fusion. So it's clean, it produces no carbon dioxide and no long-lived radioactive waste. It's safe, so there's no risks of meltdowns or anything like that. The fuels, as we mentioned in the video, are abundant. Just 1 kilogram of fusion fuel produces as much energy as 10 million kilograms of fossil fuels. So it's a very source, so you can get a lot of energy out. And the studies suggest that it could be competitive, that the economics are favorable. So where does it fit? Well, first of all, for the context, we're not on track in reducing global carbon emissions. The Global Carbon Project shows that global emissions are following the worst of the IPCC scenarios. So if you can see in this graph here, the little red dotted line is just about tracing the worst estimate, looking at the highest amount of warming. And we also know that energy is only predicted to rise in coming years, particularly as developing countries develop. So energy demands are just going up. The global economy is moving towards high electrification. So in the UK, power demand could double by 2040, with the requirement of another 300 terawatt hours of electricity supplies required. Fortunately, renewable energy generation has increased significantly, so we are able to cover some of that. You can see in the graph on the left some of the different sources of renewables and how much they've increased over the years. But we do need a mix of clean sources, including non-variable ones. So renewables are variable in that when the sun's not shining or the wind's not blowing, you don't have any energy. So you need to accommodate for that. But for a grid, to enable us to have electricity on the grid, you can't have 100% renewables, because in order to cover all the demand, you'd have to build in so much redundancy that it would be uneconomical. So you do need other sources complementing the renewables, and these would be non-variable ones such as fusion or nuclear power, or even fossil fuels with carbon capture and storage, but something that's non-variable. And there are also, we need sources to provide heat for heavy industry, because there are various industries where it's difficult to eliminate the carbon dioxide. For example, cement, iron and steel, these are industries where there's renewables are not able to eliminate those CO2 emissions. So fusion does fit into the energy market as clean, safe, sustainable baseload power, as a complement for renewables for a reliable electricity grid, and as a process heat for heavy industry. But so now I think is a really exciting time for fusion. I think over the next decade particularly, it's going to be really, really interesting. So I'd like to tell you why I think that. But firstly, let me say that we've been researching fusion for a long time. Since after the war in the 1940s, people have been studying fusion, and it's taken a long time, and that's because fusion is really hard to do. Essentially, you're trying to make a little star on Earth, and you can't just put a star in a box. It's not simple. You need to somehow get the fuel, which will be in a plasma state if it's heated to stellar temperatures, and you have to somehow confine it, and you need to stop it from touching the walls of your machine, because otherwise the walls will get hot and the fuel will get cold and then nothing happens. So you need to find some way of keeping your fuel trapped and keeping the fuel hot enough for long enough for fusion to occur. And this is understandably very tricky. But now there are various things, various factors that are coming together. One is that we have mature science. So over these decades, we've been researching fusion. We now have a very good understanding of the plasma physics. We also have an understanding of some more fusion-specific things. For example, tokamaks are a type of fusion device that is very well understood, and we've become close to exceeding energy break-even, which we call Q=1. That means getting more energy out of the reaction than we put in. And obviously this is really important if we want to make a power station. So there's been a lot of research done over the time. Now we also have enabling technologies. Technologies are developing all the time, of course, but now there's quite a few different things are coming together. One, we've got high performance computing, including machine learning and artificial intelligence. Computing is important because if we can run simulations of the plasma, which can be very, very complicated, we can better understand what's going on inside the plasma and what's going on inside the wider fusion machines. People now are also using artificial intelligence and machine learning to look at different scenarios to optimize the design of the machines or the control of the plasmas. So there are various ways that computing is coming into to fusion to improve performance. And in fact, the article that's in New Scientist this week is all about artificial intelligence and how it can contribute to fusion. So it should be an interesting read. Another thing is high temperature superconductors. So I'm going to talk more about this during the talk. So superconductors are important for fusion because if you want to keep, well, for some devices in fusion, if you want to keep using magnetic fields to trap a fusion fuel, you need to create magnetic fields continuously. And we do that using electromagnets. And if you use something like copper, it heats up very quickly and it limits the amount of magnetic field you can, or the amount of time you can create a magnetic field. So superconductors are important because they can keep running continuously. And high temperature superconductors are a newer development which will enable us to make higher magnetic fields. So as I said, I'm going to talk more about this later, but this could be a game changer for fusion. Other things are the efficiency of lasers is improving, which will contribute to laser fusion concepts. And also advanced manufacturing. So this could help to bring the costs down for production, which will make it easier to commercialize fusion. Another factor is climate change and the increasing urgency to address this issue. We've been seeing things like extreme weather events. There are also now public calls for action, such as Extinction Rebellion, Greta Thunberg. So there's a greater desire for sustainability all around, and businesses are pushing that, and the general public are pushing that as well. And so there's a need for new energy options. And so this need for new energy options is also driving private investment. We've seen increased private investment in fusion over the last decade or more. And we've also seen a lot more private companies coming into the field. And that's interesting because they all contribute to the knowledge base in fusion. And the Fusion Industry Association was founded in 2018 as more and more private companies have come about. And so we're supporting the private industry and helping to drive towards commercialization. So this graph here just shows the number of companies pursuing fusion energy and how it's increased, particularly over the last 10 to 15 years. And this to me is a key point, and it's really positive because it shows that there's increasing will to get fusion done. And so I think that, well, the other thing is, as well as the increasing will, the private companies bring a different dynamic into the fusion sector because they're not just thinking about the science, they're also thinking about the pathway to commercialization. So that's why I think that the next decade is going to be a really, really interesting one. So as I said, all these things coming together and hopefully we'll be getting towards commercialization. So now let's have a quick look at the fusion science. So fusion is a nuclear reaction. It's the cores of atoms coming together. So in the sun, hydrogen fuses to make helium. So fusion is like building blocks. You start with small particles and you build them up to make bigger and bigger ones. And that's what happens in the sun. And that's how all the atoms in all the elements in the universe were made, by building blocks coming together. So in the sun, the basic fusion reaction is that 4 hydrogens come together to make helium over a 4-stage process. And what they found out in the 1920s was that if you weigh the hydrogen that you start with, the 4 hydrogen atoms or nuclei, and then you weigh the helium at the end, you find that the hydrogen actually weighs more. So somehow, in putting these 4 hydrogen particles together, you've actually destroyed some mass. And it was Einstein who said that energy and mass are equivalent. So you're probably familiar with his equation, E = mc squared. This just says that the energy that we get out is equal to the change in mass multiplied by the speed of light squared. And the speed of light is a really big number. It's 300,000 kilometers per second. So the speed of light squared is an even bigger number. So all you need is a tiny, tiny change in mass, and you can release a huge amount of energy. So that's why fusion releases so much. On Earth, we need to do things slightly differently. We start with slightly bigger building blocks. So we fuse deuterium and tritium. These are both types of heavy hydrogen. And from that, we get helium and a neutron. And the helium stays in the machine, and the helium heats up the plasma, and the neutron will fly out of the machine, and we can extract the energy from the neutron. Now, you need really high temperatures to get fusion to happen. This is why it happens in stars. And that's because these particles that you're trying to fuse together are both positively charged, and they don't want to come together. They repel each other, like if you're trying to get 2 north poles of a magnet to come together. So you need to get them really fast. You need to get them really hot, so they're moving fast. And that's when fusion reactions can occur. So we need temperatures of above 100 million degrees. So now I want to have a look at a few different approaches to fusion, and then focus in on the tokamak, which is the best performing of all the approaches so far. But first of all, I have a short video for you about the fusion conditions and the different ways of achieving fusion. Oops, where's the video? See if this works.
In order to get fusion reactions going, you need to keep your fuel hot enough and dense enough, like the center of a star, and you need to keep it like that for long enough for fusion reactions to occur. This is encapsulated in something called the fusion triple product, N-T-tau-E. Density, temperature, and the amount of time the energy is trapped are all multiplied together, and this needs to be bigger than a certain number to achieve fusion ignition. Tokamaks have shown good progress over time. But there is wiggle room. We could have higher density and lower temperature and a long, long time, like in the sun where hydrogen fuses to make helium. Or on Earth, if we fuse heavy hydrogen, we need higher temperatures, so can have lower density and a shorter time and still get to fusion conditions. This means that there are various different approaches when it comes to fusion, and various different designs of fusion machine.
How many ways are there to achieve fusion that can give you net energy gain and have it be a possible way to produce electricity? And maybe half a dozen ways so far have achieved really truly fusion relevant conditions.
There are 2 main ways of confining or trapping hot fusion fuels. These are magnetic confinement and inertial confinement. Magnetic confinement uses magnetic fields to trap the hot fusion fuel, usually in a machine called a tokamak, or sometimes a stellarator. Inertial confinement uses a fuel pellet's own inertia, that is, its inability to move away fast enough to keep the fuel trapped and hot. Intense laser beams compress a tiny fuel pellet to obtain fusion conditions in the center of the pellet. Others use shock waves. The most heavily researched approaches are tokamaks on the magnetic side and laser fusion on the inertial side.
A fusion plasma is a fusion plasma. They might have slightly different collisionalities and need slightly different theoretical models. But in the end, the foundational science is very much overlapping. Certainly, I worked myself most directly in magnetoinertial fusion, and we very much use the same theoretical constructs and modeling tools from both sides. So I do think there's a strong overlap in the science.
Historically, government funding was channeled into these two main approaches, which has resulted in some very large, impressive facilities like JET, ITER and NIF. The JET tokamak currently holds the world record for fusion power produced. Also, a lot of research has gone into understanding the fundamentals of fusion and plasma physics, as well as the specifics of these approaches. But there are other possible ways of achieving fusion. Other methods being investigated are magnetized target fusion, the field reverse configuration, the sustained spheromac, the dense plasma focus, the sheared flow stabilized Z-pinch, and more.
Having a lot of approaches is a good thing for fusion. It diversifies the risk because a lot of the concepts have different risk profiles. They have different reactor engineering requirements, and also pursuing multiple approaches actually, it cross-fertilizes ideas at this point, which I think is useful.
So that gives you an idea of the different ways that we can go about achieving fusion. But as I said, the best performing is a tokamak, and also a tokamak's what I know about because I did my PhD on tokamak. So I'm going to talk a bit more about the tokamak. So what is a tokamak? It's just a way of trapping our fusion fuel and heating it to fusion conditions. So the word tokamak is actually a Russian acronym. It stands for Toroidalная камера магнитная катушка, which is a bit of a mouthful. But I like it because it actually explains exactly what or describes exactly what a tokamak is. It means toroidal chamber magnetic coils. So you've got a toroidal or a ring donut shaped chamber with magnetic coils that make a trap for the fusion fuel. So what you can see in this picture here is the blue coils around the outside. They make a magnetic field that goes through the pink plasma in the middle around the long way around the donut ring. And then there's also a current that flows in the plasma around that way and around the long way. And that makes another magnetic field around it, the green arrows going in the short way around the donut. And they sort of pull the plasma away from the wall. And then the gray coils that you can see, those are used to shape the plasma. They create a magnetic field around them that can kind of push in on the plasma. So you can push them from the top or push from the bottom, and you can move the plasma or shape the plasma. So that's the basic interior workings of a tokamak. Of course, it gets much more complicated than this because you have heating systems and you have diagnostics so that you can look at the plasma and see what's going on. But this is the basic inner workings. So this is the Joint European Torus, or JET, which is at Culham Laboratory in Oxfordshire. You saw this in the video. This is what it looks like on the inside of the ring, and it's quite big. A man could stand up in there very easily with lots of room. It's about 12 meters in diameter across this ring. So you can see on the left side, that's what it looks like with when it's empty, and on the right you can see there's a plasma inside. And you'll notice that it looks like there's nothing there in the middle. It's all sort of invisible, and that's because in the center of the plasma, it's so hot that it's only emitting light in the X-ray or the ultraviolet part of the spectrum. So all we see is the cooler stuff around the edges. So the cool stuff is where it's emitting visible light. So that's all that we can see. Then there's also a variety of tokamak called the spherical tokamak. And a spherical tokamak is just a tokamak that's been squashed up. So rather than looking like a donut shape, it looks more like a cored apple. It's all been squashed into the center. And spherical tokamaks are interesting because they have several advantages. Firstly, they're more efficient than conventional tokamaks. This is a parameter that we call beta, and it's the ratio of the plasma pressure to the magnetic pressure, the magnetic field that's confining it. Spherical tokamaks are also better at keeping the plasma hotter for longer. So that's the tau E measurement. And And this is important because you need to keep your plasma hot enough for long enough to get fusion reactions to occur. Spherical tokamaks also suffer less from instabilities. Now, the plasma is a fluid. It can be quite turbulent, and there are lots of little eddies and whirls inside it. And instabilities can be problematic because, firstly, the instabilities cause the heat to leak out faster. We don't want that to happen. And secondly, if you get a big instability, which causes us to lose control of the plasma so it hits the wall, then you can get what's called a disruption, where you lose all the heat from the plasma and you have to start again. So we don't really want instabilities. So that is a good thing that they suffer less from instabilities. And also, which is another thing which is important, is that they require less energy to drive that current that goes around the inside of the plasma, which helps to stabilize the plasma. And this is something called the bootstrap. Well, the bootstrap current is something that's a self-generating or self-driving current inside the tokamak. And this is really important because it relates to the efficiency of a future power plant, because in order to create that current, you need to put energy in. And if you're making a power plant, you want to get as much energy out as possible and put as little in as possible. So this is important for future power plants. There is a disadvantage to spherical tokamaks, and that's that they're so squashed up that there's less space in the center. So the engineering is trickier because everything's a bit more compact and squashed up. But the advantages do make up for that. So the spherical tokamak was pioneered at Culham in the 90s, and that's something that Tokamak Energy are taking forward, which I'll talk about later. But first of all, is bigger better? So you heard in the video that historically tokamaks, fusion machines, have been getting bigger and bigger. I want to have a little look at why that is. So first of all, let's have a look at this equation. This just tells us that the fusion power that we get out is related to various different parameters, and particularly these three. One is the efficiency of the machine, the plasma beta. The other is the magnetic field strength, or B, and the other is size, or volume. So increasing any of these three things will increase the amount of fusion power that we can get out. Now you can see from the numbers there, the powers, that the magnetic field strength has the greatest effect, then the efficiency, and then the volume. Now, historically, some of these things were difficult to increase. So the efficiency is pretty much fixed in a conventional tokamak. It's difficult to increase that very much. The magnetic field strength is limited by the technology of the time, what kind of magnets that you can produce. And also the magnetic field strength is the expensive part of the tokamak generally. So it was also difficult to increase the magnetic field. So volume is the easiest parameter to play with here. You can increase the size of the machine, and that increases the amount of time it takes for the energy to leak out, and that should help you get more fusion power. So that's what happened. The machines got successively bigger and bigger, and now ITER is under construction. Currently, it's in the south of France. So ITER is about 2 or 3 times bigger than JET. So JET was already quite big, about 11.5, 12 meters tall. ITER is going to be about 30 meters high. So it's a really big machine, and it's an incredible feat of engineering. Just as a comparison, this is one of the toroidal field magnets. So one of those blue coils that were in the basic tokamak diagram. And ITER will have 18 of these toroidal field coils, and just one of these coils weighs the same as a fully loaded Boeing 747. So, as I said, it's a huge machine. It's an incredible feat of engineering, and it's under construction right now. So if you go on their website, you can see pictures and videos of the different parts coming in from all around the world, because ITER's a worldwide collaboration. And so, yeah, you can see all these bits coming in and things being assembled. So it's due to finish construction about 2025. However, new technologies can change the picture. So if we go back to that equation, if we can find ways to increase the efficiency or the magnetic field strength, then we don't have to increase the volume so much. So we can make smaller machines. And so the efficiency, we find that spherical tokamaks have a higher beta. So that's one way of increasing the efficiency. The magnetic field can be increased using high temperature superconductors, which I talked about earlier on. So high temperature superconductors are, I think I've got a tape picture here. Here we go. So this is a picture of a high temperature superconducting tape. It's actually a ceramic that is deposited onto a tape, and because it's been deposited onto a thin tape, it's possible to wind it into coils, and that's how we make electromagnets that we can use for fusion. So this is a relatively new development, being able to fabricate the high temperature superconductors as tapes. And high temperature superconductors are able to carry a lot more current than even low temperature superconductors, and definitely higher than copper. And so that means that they're able to make much higher magnetic fields. In fact, if you look at this picture here and you see the size of the tape, if you got a piece of copper the same size as that, and you put the amount of current through the copper as you can put through that high temperature superconducting tape quite happily, then that piece of copper would vaporize in under a second, fractions of a second, because that's how much current the high temperature superconductors can carry. So they enable us to make much higher magnetic fields, or improved magnets, and that means that we don't have to increase the volume or the size of the machines so much. Now, of course, there's more to that. You don't actually need to look at the more important parameter is not so much the fusion power that you get out, it's the energy gain that you get out, so how much excess energy you're able to get. So you don't necessarily need to make hugely powerful machines. You can make lower power machines as long as they're getting significantly more energy out than is put in. So that's something that's being investigated as well. There's also now research that shows that fusion machines don't have to be big. So back in 2015, one of our physicists, Alan Costley, who spent his career working on the jet and jet tokamaks in ITER, he published some research that showed that there's nothing in the physics that says that fusion machines have to be huge. And this is really interesting because he said that it's not the physics as such. The size of the fusion machine depends on the approach adopted, on the engineering, and on technologies. And this is interesting because technologies always change. So I think it's really positive and really hopeful, because it means that we don't have to keep going bigger and bigger. We can have an aspiration to make smaller, more compact, cheaper machines. And just because we can't do something right now doesn't mean that technologies won't change in the future to enable that. So Tokamak Energy is working on what we call a compact modular fusion solution. So compact in that the machines are going to be smaller than something like ITER, for example, and modular in that we'll make smaller, lower powered modules that can be grouped together for different sized power plants. And this has a variety of advantages. One is that if you can make smaller machines, they're easier to commercialize. They open up the possibility of factory production, which means that they're easier and cheaper to build. They also, in modules, grouped in modules, they give more flexibility in how power plants can operate, because it wouldn't be a simple on or off. You've got more nuance in the amount of energy that you can produce. So you could just be using 1 or 2 modules, or you could ramp it up to 8, for example. And it gives there's space for a bit of redundancy. So if you need to make repairs to one of your modules, you can do that where you've still got others operating. So we believe that a modular solution is a good one. So let me now focus in on some of the work of Tokamak Energy. So Tokamak Energy is building on the work that has gone into JET and ITER on tokamaks, but supplementing that with new technologies. And so they're using spherical tokamaks, which I've mentioned, and high temperature superconductors. So spherical tokamaks which are more efficient, high temperature superconductors to make higher magnetic fields. And you can combine these two things together to enable us to make smaller machines and therefore be able to build them cheaper and faster. Tokamak Energy was founded in 2009 as a spin-out from the Cullum Centre for Fusion Energy. Since then, they've raised over £100 million, and they've built and tested 3 prototype tokamak devices. They now have a team of over 100 people, including leading physicists and engineers, and they filed over 50 separate patent families. So I'm going to go through some of the things that Tokamak Energy has been doing over the last decade. So they started off with a small tokamak called ST25. So this is ST25. It's about the size, like, you could almost, if you had a really like wide arms, you could almost put your arms around it. It's that kind of size. And this was just to demonstrate their capabilities, that they could build and operate a tokamak. And then they went on to put high temperature superconductors around this size of tokamak. So this ST25 HTS tokamak was the first tokamak to have all its magnets made of high temperature superconductors. And this demonstration in 2015 was when they held a plasma there for 29 hours before turning it off. So it wasn't a high power fusion plasma, but you can see the pink glow there inside the tokamak. And it was a demonstration of the magnets and the fact that we could use this really new material, this high temperature superconductor material, to make tokamak magnets. From there, we were building another tokamak, a bigger tokamak called SD40. This is one of the early design drawings, and that's one of the founders, Alan Sykes, pointing at a coil in the middle of the machine, or not in the middle, but inside the machine, a merging compression coil. And this is a short video that, or not, it's a clip from one of the videos that we've got on YouTube that just shows how the little different pieces of the tokamak come together. Sorry, the clicker's not allowing me to play the video. I've got to do it here. Where is it? Oh, go back. Sorry. I can't see where the video is. Where is it? Oh, there it is. Okay.
So those are all the important components of ST40. Here's how they'll be assembled. The inner vacuum chamber with the merging compression and diverter coils. The center column and solenoid that slots down the middle. Next come the return limbs and their supports, followed by the outer vacuum chamber and the remaining vertical field coils. This will be ST40, the world's first compact high-field tokamak.
All those videos are on YouTube, by the way, so if you want to see the full videos of that, which is all about ST40 coming together, then that's on our YouTube channel, along with lots and lots of other things. So do go and check that out. So this is the construction of ST40. This is the very inner central vacuum vessel that looks like a bit of an egg. And then the coils, the toroidal field coils, get put on around there. These ones are copper. So ST40 is a copper tokamak. We're developing high temperature superconductors in a separate program alongside, but SD40 is a copper coiled tokamak. This is the outer vacuum vessel, which will enclose the whole machine. This is the outer vacuum vessel being put on, so you can see the inner vessel there in the center and the coils around the outside, and then the outer vacuum vessel. And then this is one of the poloidal field coils going on, so that's the coil that shapes the plasma and moves it around. And this is a picture of the tokamak put together, not fully constructed, but operational. This is a picture of the inside of the tokamak. So you can see here there's a plasma forming in wisps around the inner coils. These are the two merging compression coils. Merging compression, I'll mention later, it's a way of starting up the plasma. And this is a picture of the plasma formed in ST40. In 2018, we hit one of our major milestones, which was to achieve 15 million degrees inside ST40. So this is hotter than the center of the sun, and this is one of our steps to getting to fusion temperatures. So our next milestone, our next aim, is to get to 100 million degrees, and that's fusion conditions. We're hoping to do that this year, coronavirus willing. Also in 2018, we moved to a new facility. Our team was growing and the tokamak was growing, and so we needed more space. So this is a picture of some of the team in 2018, and it's grown a lot since then already. Like sometimes we're getting 1 or 2 people a week. This is a video I'm going to find it. Can't see my mouse. This is the construction of SD40. So it's being put together again or reassembled in the new building in 2018. So you can kind of see how it comes together. This is the control room in the new facility. And this is a video of one of the plasma, a plasma in jet, sorry, not jet, plasma in SD40. Where is, I can't see there we go. So the plasma starts up around the inner coils, and then it is squashed together and formed into a ring. So the main plasma is inside that orange outline. So that's one of the experiments on SD40. And this was the tokamak in 2019. So it's constantly being worked on, like adding new systems to improve the performance. So there's a lot going on SD40. And SD40, as well as hoping to demonstrate fusion conditions in a small tokamak, it's also researching new plasma physics. It's a world-class research tokamak. It's the world's highest field compact spherical tokamak. And it's also been doing studies of merging compression. So it's studying how the plasma behaves in this high field compact shape, and also looking at different ways to start up the plasma. So merging compression is a way of starting the plasma without using the central solenoid. So most people, most tokamaks, use the solenoid in the center. But because of the space restrictions in spherical tokamaks, it would be advantageous to not use a solenoid. So that's something that we're investigating. The way merging compression works is you start with two rings of plasma that start up around the inner merging compression coils. And then these are pushed together and they combine into one blob, as you can see in this picture. And what happens is when those two rings combine into one, magnetic fields have to break and rejoin. And this is a process called magnetic reconnection. And it releases huge amounts of energy. It's seen in nature on the sun. It makes solar flares, and also in the Aurora. And so people, scientists like to study magnetic reconnection for that reason as well. But it really releases a huge amount of energy. And so the 15 million degree temperatures that were achieved were done using merging compression. Now we're putting other heating systems on to get us to 100 million degrees. In 2019, we announced the progress of our magnet development program. They've been making rapid progress, and they've been making small coils that you can see in this picture with the high temperature superconductors. And they achieved a peak magnetic field on the coil of 24.4 Tesla, which is a world record. And they've also found that the magnets are extremely robust and reliable, and they're simple to manufacture. So the HTS program is well ahead of schedule, and they're now working on producing a tokamak magnet from these high temperature superconductors. So the big question that you're probably all asking is, when will we have fusion? And of course, this is like an impossible question to answer, because it depends on so many things. It depends on people, money, politics. It's not just the science. Of course, I can give you some targets and some aims, but this is science, it's an exploration. It's never been done before, so it's impossible to give timescales or exact timescales. So Tokamak Energy has some various steps to fusion and different aims. So the first one is but the current status is that we've got SD40 and we're operating SD40 and aiming to get to 100 million degrees, hopefully this year. At the same time, we're working on a high temperature superconductor magnet demonstrator. So that's a large scale high temperature superconducting magnet that could be used for tokamaks, demonstrate the feasibility. Then those two strands will come together into our next machine, which is called STF1 for fusion power. And so STF1 will be constructed by 2025, and STF1 aims to get more energy out than is put in, so get past energy break even. This will be a key moment for fusion. Some people refer to it as the Wright brothers moment or the Kitty Hawk moment. It's like when the plane starts flying for the first time. It will really prove that fusion can be done and can generate power. And then after that, by 2030, Tokamak Energy hopes to build a commercial scale module, STE1, which will provide electricity. So those are the Tokamak Energy aims. By 2030, we should also hopefully see ITER operating. It's aiming for first plasma around 2025, 26. So ITER should be operating, although they don't have plans to do break-even experiments until inside the 2030s. So we'll have to see how that goes. Also, there are other startups working on fusion, and this is some of the logos from some of the members of the Fusion Industry Association, which, as I said earlier, it's growing all the time. They range from small startups to some really quite big, well-funded startups. So, well, they're not really startups anymore, really quite big, well-funded companies. So it'll be interesting to see what happens with the other fusion private companies in the next decade too. And what can you do if you're a supporter of fusion? Well, we need to build something of a fusion movement, tell people about fusion. We need to raise awareness of fusion, that it's coming, what its benefits are, so that people know what it is. You can educate young people about fusion, quite similar to the previous one, really, but the young people are the ones who are going to be living with fusion in their futures. And so tell them about it, educate them, let them know what it is. You can follow the Fusion Industry Association and various fusion companies on social media. There are YouTube videos, Twitter, that kind of thing. So keep up to date with what's going on. And also you can demand change from government. I think that it's a really interesting time now, particularly as we start emerging from the pandemic. We've got an opportunity to make changes, to invest more in green technologies, to not go back to the old ways. We all know that the change has to come, so let's all start demanding more of that change from government and get more support into new energy technologies. So in summary, what are the little takeaways here? Fusion is the energy of the stars. It's needed on Earth for clean, reliable baseload power. The science of fusion is mature. There are new technologies that are changing the possibilities. Climate urgency is rising, and private investment is moving the field towards commercialization. So all of these factors are making it a really exciting time for fusion right now. And I think that the next decade is going to be very interesting indeed. Tokamaks are the best understood of all fusion approaches. Tokamak Energy is building on the JET and ITER research and bringing in new technologies to enable compact, modular and economical fusion power. Tokamak Energy and other startups hope to demonstrate the commercial feasibility of fusion by 2030. So now is a crucial time as we move into the era of commercial fusion. We're going to need dedication, investment, smart people, and public support. So I hope we have yours. Thank you very much.